Welcome everybody. Welcome everybody. Our guest speaker is Dr. Karim Mosani, and the title of his talk is Geometry and Topology of Trapped Photon Region in a Class of Stationary Spacetimes. Please, Karim, begin your talk.
Thank you very much, Professor Paikovsky, for having me here. And also, I would like to thank the participants in the audience for listening to this talk. So, I'm Karim Mosani. I'm a postdoc in Tuebingen University. And the work that I'll be presenting today is jointly done with Professor Carla Sederbaum, who is also affiliated to Tübingen University. And the title of my talk is Geometry of Trapped Photon Region in a Class of Stationary Spacetimes. So we will see in the talk what we mean by trapped photon region and what do I mean by the geometry of trapped photon region. So let's begin. This is the outline of my talk. First, I will discuss a few definitions and terminologies that will come into picture while defining the problem. And once we are done with that, I will discuss some existing work in the literature. And then uh, after this, I'll discuss what is the aim or motivation of doing this work and how our work fits with the existing literature. And then I will discuss the main result of our work. And finally, I will discuss the sketch of the proof of the main result. So let's begin with the very well-known Schwarzschild spacetime. So it is a static, asymptotically flat, spherically symmetric solution of Einstein vacuum equation, and it is given by this tuple curly m comma g. And for a given positive real number m, this curly m is as shown over here, and the g, the spacetime metric, is as shown over here. And tr theta phi is of course the coordinates of curly m. And as you can see, the set R equal to 2m is not included in this curly m. So you have an open interval 0 to 2m, union 0, 2m to infinity, open interval. So however, we can include this set R equal to 2m by choosing suitable coordinate systems that we call as Kruskal-Zekeres extension that we won't discuss further in this talk. So this, physically speaking, Schwarzschild spacetime is models a static non-rotating black hole. And the rotating counterpart of Schwarzschild spacetime is the Kerr spacetime. So you have two parameters, one real number A and one positive real number capital M. And uh, let us consider the spherical polar coordinates on S2 and define this two function rho and triangle. And in terms of these two functions, let us write the spacetime metric as shown over here. And from this curly M, remove the set capital C, which is defined as the collection of all the points in curly M, such that this metric G with subscript capital M and A is not Lorentzian on the tangent space of curly M at point P. So let's remove this entire set C out of curly M and obtain a new smaller set that we denote as curly M with the subscript capital M and A, and the tuple is called Kerr spacetime. So physically, this models a rotating black hole spacetime, which is asymptotically flat, stationary, axisymmetric, and solution of Einstein's vacuum equation. The next definition is okay. I would like to tell you one more thing. Please feel free to interrupt me in between the talk if you have any questions or doubts or suggestions. So the next definition is the killing horizon. Let's fix a killing vector field x in the uh, in gamma Tm, and corresponding to this killing vector field x, this particular set n with subscript x is called the killing horizon. So it consists of all the points in the space-time such that x is null on that points. The collection of all such points is the killing horizon. Now, in terms of killing horizon, we can define what is known as black hole horizon. So at least in stationary settings. So black hole horizon is smooth, closed, oriented, two-dimensional embedded surface in the space-like hypersurface such that it is a stationary killing horizon. What do you mean by stationary killing horizon? It is a killing horizon corresponding to stationary killing vector field. And what do you mean by stationary killing vector field? It is a vector field, killing vector field corresponding to stationary spacetime. Now,
Ask a question.
yes.
Uh, so uh, perhaps I'm missing something in your definition 3, but
Okay.
it seems to me that are you also assuming that the surface N is a null surface
Uh, the
and
surface.
that N that X is so for me killing horizon is when is a null surface
Yeah.
such that the killing vector is tangent to this surface
Yeah.
and orthogonal at the same time.
Yes, exactly. I think then it overlaps with this definition as well. So, uh, also, I would like to mention that there is an abuse of notation over here. So, the x over here is the vector field, but the x over here inside this set is a vector. So, yeah, this is the abuse of notation. And the definition that you gave for killing horizon overlaps with this definition over here.
I see. So, what about the boundary of the? What about the ergosphere? Is ergosphere a horizon for you? On
Uh,
er, on ergosphere, the vector field d upon dt is null.
yeah. Uh, uh, okay. Mm, so that killing vector field is null on the ergosphere. And yeah, I think according to this definition, that also is a killing horizon, but I'm not very sure about it. Maybe I am missing something in this definition, so I'm not very sure about it.
So usually,
Yeah,
our colleagues who do mathematical relativity, they assume that x is null on p and at the same time it's tangent. I mean, it's null to n, is
yeah,
null at n and it is tangent to n.
yeah,
Or in other words, that the pullback of metric tensor to n is a degenerate metric
yeah.
and
Mm-hmm,
x is pointing in degenerate direction of this metric.
mm-hmm. Okay, okay. I'm not very sure about the ergo region, but maybe I can answer your question once I figure this out. Uh, and
Okay,
as
please go
Yeah,
ahead.
yeah. Okay, okay, fine. Thanks. And as far as the definition that you said for killing horizon, it overlaps with it seems to overlap with the definition that is written over here, I suppose. Okay, so let's move on to the next definition that is of black hole horizon that is defined in terms of killing horizon. And it is smooth, closed, oriented, two-dimensional embedded surface in the space-like hypersurface such that it is a stationary killing horizon. And by stationary killing horizon, I mean killing horizon corresponding to stationary killing vector field. Examples of black hole horizon are the R equal to 2m in Schwarzschild spacetime, as we all are aware of. And in Kerr spacetime, it would be this triangle equal to 0, or equivalently, this R equal to capital M plus minus of the square root term. You can see that in Kerr spacetime, if this A is less than M, then you could have two black hole horizons. In such case, you say that the Kerr spacetime is sub-extremal, and in the case A is equal to M, you have just one black hole horizon, in which case you say that the Kerr black hole is extremal, and if m is less than a, then you don't have a black hole horizon, and what you get is a naked singularity. And also, I would like to mention that this parameter A is called rotation parameter. It tells you about the rotation of the black hole. So if you substitute A equal to 0, you end up with Schwarzschild spacetime. The next definition that I would like to discuss is the domain of outer communication. And here I would be discussing the imprecise definition.
Regarding your definition of black hole horizon, so some spacetimes consider cosmological horizon. For instance, de Sitter spacetime. So
Yeah.
would you is a two-dimensional section of the cosmological horizon in de Sitter spacetime is a black hole horizon according to your definition 4?
Uh, if it is a stationary killing horizon and it is a space-like hypersurface, then yes. Uh, uh, yeah. If it is stationary killing horizon, then yes, it would be. Uh, uh, hmm, but in that case, we will then have to uh, mm, refine the definition so that you don't consider the cosmological horizon as the black hole horizon. So, yeah, I think we will then have to refine the definition to be more specific.
Okay, please go ahead.
Okay. Okay, fine. So also this definition is restricted to stationary settings, only stationary spacetimes. And yeah, maybe if you don't want to consider cosmological horizon as a black hole horizon, then you can also add one statement of asymptotic flatness. So then if you add this additional word, then the cosmological horizon in the de Sitter space that you mentioned won't be the black hole horizon, I guess. Okay. Okay, so let's move on to the next definition, that is the domain of outer communication. And uh, this is the imprecise definition. I have added the more rigorous, precise definition in the appendix. So if anyone has interest and if we have time, then we can discuss the precise version as well. So, but before that, uh, let us discuss one more thing, a property of the space-time called global hyperbolicity. So if you have this property of the space-time, then you can decompose the space-time into two components, sigma cross r. Sigma is the space-like hypersurface, and it is also called as Cauchy surface. And uh, so let us look at this example, this diagram over here. This is the diagram of a black hole horizon in Schwarzschild spacetime. So let us imagine this XY plane as the space-like hypersurface, and this circle is the black hole horizon. And you can evolve this black hole horizon in time in case you have globally hyperbolic spacetime. Then this hollow cylinder is what is called the evolution of the black hole horizon. And the region outside the evolution of the black hole horizon is the domain of outer communication in case of Schwarzschild spacetime. So we can extend this definition to stationary axisymmetric spacetimes as well. And the examples of domain of outer communication is R is greater than 2m in Schwarzschild spacetime, and R is greater than the outer black hole horizon in case of Kerr spacetime. And if you have the rotation parameter greater than the mass parameter, then the domain of outer communication is the entire Kerr spacetime. The next definition is the trapped photon in stationary spacetime. So in Schwarzschild spacetime at r equal to 3m, you have photons that orbit around the center, and these photons neither fall into the singularity nor escape to nor escape to infinity. And such photons are called trapped photons. So in 2019, Sederbaum and Jans proposed a definition of trapped photon in stationary spacetimes. So a photon with the property that its orbit in the quotient of the domain of outer communication under the action of stationary killing vector field is contained in a compact set. If this property holds, then the photon is called trapped photons. So in order to understand this definition, let us look at this first diagram. You have the evolution of the black hole horizon, that is this hollow cylinder, and this green colored spiral is the trapped photon. Now, uh, now in the next diagram, if you can see these lines, you identify all the points in the given line and obtain the quotient set of the domain of outer communication as shown in the third figure. And in this quotient set, the trapped photon is this green colored circle. And uh, yeah, of course, the photon, if it is contained in the compact set in this quotient set, then you call that photon as trapped photon. And the union of all these trapped photons is called trapped photon region. Now let us move to the next section, that is of the existing work. Uh, I'll just move this slide down. So, as I said before, in the domain of outer communication of Schwarzschild spacetime, you have unstable circular orbits of trapped photon at r equal to 3m, and this unstable circular orbits, the collection of all such unstable circular orbits uh, form a three-dimensional time-like submanifold of the Schwarzschild spacetime, and it has a topology S2 cross R. And this collection union of all these trapped photons in Schwarzschild spacetime is called the photon sphere. Now, let us look at the Kerr analog. So in Kerr spacetime, sub-extremal Kerr spacetime, where the rotation parameter is less than the mass parameter, you have trapped photon region in the domain of outer communication, and it looks like this as shown in the figure in space-like hypersurface, the gray colored crescent moon part. And it turns out that unlike the case of Schwarzschild spacetime, in Kerr spacetime, you don't have a trapped photon region as a submanifold of the spacetime. It is a subset, of course, but it is not a submanifold. So intuitively, you can see these two pinches in the north and the south pole, and hence the the trap photon region is not a submanifold. It does not have a smooth structure. However, smooth structures are desirable, and it has some applications that we would see further in the upcoming slides. But before that, uh, l- let me discuss one thing. Consider a geodesic in the space-time, gamma. This geodesic can be identified by a point, an element of the tangent bundle. So how can you do that? Consider gamma in the spacetime. Gamma is the geodesic. And if I have these two numbers, gamma at a point and the tangent of gamma at that point, then I have the information of the geodesic. But these two numbers, this tuple, is an element of the tangent bundle. So under this canonical map, you can identify each geodesic in the spacetime as a point in the tangent. So, and using this canonical map, one can lift the union of all the trapped null geodesics, that is capital P, to the tangent bundle, and we call this lift of the trapped null union of trapped null geodesic to the tangent bundle. We denote it as P tilde. Okay, and in the case of sub-extremal Kerr spacetime, we have this following result that was by Sederbaum and Jans in 2019. And the similar result was obtained in 2015 by Diatlo, but the approaches in both the approaches are different. So in Sederbaum and Jans 2019, this is what they found. In the case of sub-extremal Kerr spacetime, the trapped photon region in the domain of outer communication, P tilde, that is the lift of trapped photon region in the tangent bundle, is five-dimensional submanifold, and it has a topology SO3 cross R2. So uh, even though the trapped photon region in the spacetime is not a hypersurface or it is not a submanifold, its lift in the tangent bundle or the cotangent bundle is a submanifold, and it is five-dimensional and with this particular topology. Now, in the next section, we discuss what is the goal of this work. The goal of this work is to generalize this result in sub-extremal Kerr spacetime to a bigger class of axisymmetric stationary spacetimes. And
Can I have a question about your
yes,
last slide,
yes,
about this topology?
yeah.
So you can act by the rescaling of the velocity for the null case. So what is the action on this space SO3 times R2? If you make the rescaling of the length of, okay, not the length, but of the null velocity. So how it's acting on this space? The action of this, so you can make the projectivization of the space of null geodesics, and then what will happen with the this space SO3 times R2?
I'm sorry, I didn't understand the question. Can you please
So,
repeat?
so I understand that this space of null geodesics,
Yeah.
you don't identify two geodesics that differ by the speed.
Yeah, of course. So you have to distinguish between different parameterizations. So same geodesic with two different parameterizations can be seen as two different points.
Yes, and
Yeah.
so how you see, so do you know the identification? Okay, so the map that sent one point into another on the level of this SO3 times R2, how these maps look like?
Uh, if you distinguish between null geodesics with different parameterization, then this map is bijective, map from the spacetime to the tangent bundle. If you don't distinguish, uh, then it is not bijective because one geodesic would be mapping to more than one points in the tangent bundle.
Okay, thank you.
Yeah. So, I forgot to mention this point that you have to distinguish between null geodesics with different parameterization, because then you can see gamma 0, gamma dot 0 would be different, right? If you change the parameterization, gamma dot would be different. So more than one point is associated to the same geodesic if you don't distinguish between different parameterizations.
Okay, thank you.
Okay. Does this answer the question, or am I did I miss something?
So, more or less, but so my question was more about whether there is a good description of this space after this identification. But okay, I understand that there's just some bijective map on this space. Okay, thank you.
Okay, thanks. Thank you. Okay, so the aim is to generalize the result by Sederbaum and Jans. Sederbaum and Jans has the result in sub-extremal Kerr spacetime. The present work is to the aim is to generalize this result to bigger class of stationary axisymmetric spacetimes. And there are some applications of this work, especially in black hole uniqueness theorems. So in 1960s or so, Werner Israel uh, he gave the first black hole uniqueness theorem, which loosely speaking states that static topologically spherical black holes are Schwarzschild spacetimes. So and then there were a lot of other statements about the black hole uniqueness theorems. They are also called as no-hire theorems. And lately, okay, so in this black hole uniqueness theorems, you identify black hole by its horizon. Now, the proposal is to identify black hole by its trapped photon region. And using this identification, people have developed black hole uniqueness theorems in terms of trapped photon regions. So, for example, in 2014, Sederbaum and again in 2015, along with Galloway, they proved the statements of this kind. Schwarzschild spacetime is the unique static vacuum asymptotically flat spacetimes that possesses a photon sphere. Then in 2015, Yazadjev he proved he proved the uniqueness of static spacetimes with photon sphere in Einstein's scalar field theory. And then in 2016, Sederbaum and Galloway extended their previous result to electrovacuum settings. In 2019, Sophia Jans proved this photon sphere uniqueness in electrovacuum spacetimes, but in higher dimensions. So generalization of this 2016 result. Now, as you can see, the statements are about static spacetimes. We don't have such statements for stationary spacetimes. So in order to develop black hole uniqueness theorems in stationary spacetimes or stationary axisymmetric spacetimes, you should have the information of trapped photon region before, and then you can go forward to develop the state black hole uniqueness theorems about stationary spacetimes, where you identify the black holes by trapped photon region and not by the black hole horizon. So this is one of the applications of studying the trapped photon regions. Another application is black hole dynamical stability. So what do you mean by dynamical stability? If you have a if you have a space like hypersurface, you give some initial data of Schwarzschild spacetime, and if you evolve this initial data, you get the Schwarzschild spacetime. Now, if you make small perturbation into the initial data and then evolve it, and if this perturbation dies out, then you say that Schwarzschild spacetime is dynamically stable. So over here, also just like the black hole uniqueness theorems, you identify the black holes by the black hole horizon. Now the proposal is to identify black holes by trapped photon region and study the dynamical stability of black holes. So trapped photon region has applications in black hole dynamical stability as well. And one more possible application would be in cosmic censorship conjecture. So in 2019, we had this image of the black hole by the image of the black hole shadow by the Event Horizon collaboration. And sometime after that, there was this paper that says that even naked singularity spacetimes could have similar shadows. Now, shadows of the spacetime, be it black hole or naked singularity, is connected to trapped photon region. So if we study trapped photon region rigorously, maybe we can find some distinction in the trapped photon region between black hole spacetimes and naked singularity spacetime. So this is one proposed application. I am not very sure how fruitful this application would be, but at least it is worthy of giving some thought. Okay, so the aim was to generalize the existing result to a bigger class of axisymmetric stationary spacetimes. What are this bigger class? There is this algorithm known as Newman-Jennings algorithm that was constructed to obtain the rotating version of Reisner-Nordstrom spacetime in 1960s or so by Ezra Newman and Jennings. So what the algorithm does is you begin with static spherically symmetric spacetime, you apply the algorithm and you obtain stationary axisymmetric spacetime, the non-rotating version. So you begin with this first green colored box that is static spherically symmetric spacetime, apply the algorithm, end up with a rotating version of that spacetime. As shown, the metric is shown in the second green box. And these terms, small f, capital small f and others, they are related to the terms in the metric coefficients of the static spacetime as shown over here. So you can obtain curved spacetime from Schwarzschild spacetime, Originally, it was used to obtain Kerr-Newman, the rotating version of Reisner-Nordstrom spacetime from Reisner-Nordstrom spacetime, and both are solutions of Einstein's Maxwell equations. And you can also obtain the rotating version of the static spherically symmetric black hole spacetime, that is a solution of Einstein-Maxwell dilaton-axion equation. So these are some known examples of the spacetimes that can be obtained from the static version using the Newman-Jennings algorithm. Our interest is to generalize the result by Sederbaum and Yas to the class of stationary axisymmetric spacetime of this kind, the second green box. So, yeah, do you have any questions at this point? Okay, I guess then I'll move forward. Uh, so let's move on to the main result of this work. Let's consider the Newman-Jennings algorithm constructed stationary axisymmetric spacetimes containing trapped photons. We now know what trapped photons is because we are referring to the definition given by Sederbaum and Jans that I mentioned sometime before. So consider a stationary axisymmetric spacetime that is constructed using Newman-Jennings algorithm and it contains trapped photons. If these four conditions hold, then the image of the trap photon region in the tangent bundle under this canonical map, under the canonical projection, is a five-dimensional submanifold of topology SO3 cross R2. So it is a statement similar to the statement of Sederbaum and Jans. Sederbaum and Jans had this statement for sub-extremal curve. Now we have this statement for uh, for a bigger class of stationary axisymmetric spacetime constructed from Newman-Jennings algorithm, along with this four uh, along with this four constraints. So the fourth constraint is the existence of black hole horizon, and the first is the second constraint is the bijectivity of K. Just to recall, K, you can see capital K over here. So in case of sub-extremal curve space, or in case of any curve spacetime, K becomes simply R squared. Now we have K as a function of R, which is bijective. So a generalization to curve spacetime. And also small f in case of curve spacetime, as you can see over here, becomes capital M R in case of curve spacetime. So now we have a function of R, f of R, that's it. So this is a generalization of the curve spacetime. However, there are some restrictions on these functions f and k as shown in 1, 2, and 3. And this superscript prime, it denotes the derivative with respect to R. So f and k are functions of R. You have these four restrictions on this stationary axisymmetric spacetime constructed from Newman-Jennings algorithm. And if it has trapped photon region, then the lift of this trapped photon region in the tangent bundle is five-dimensional and has this topology. Any questions at this point? Okay, I'll move forward then. So let's discuss the sketch of this statement and sketch of the proof of this statement. And we adopt the methodology of Sederbaum and Jans, the methodology that they used to prove their statement for sub-extremal curve spacetime. We adopt this methodology to prove our statement for bigger class of spacetimes. So the proof is divided into three parts. The first part is studying the trapped photons in the spacetime. Second part is lifting the trapped photons, the entire trapped photon region, to the tangent or cotangent bundle, or we also call it the phase space, and studying the geometry part. And then finally, the third part is to study the topology of this lifted trapped photon region in the tangent cotangent bundle. So let's consider the first part of the proofs, that is studying the trapped photons in spacetime. Uh, you have some symmetries in the spacetimes that we are considering. So we have stationarity, axisymmetry, and we also have a hidden symmetry that is due to the killing tensor field. So, for example, in curved spacetime, you have a conserved quantity, or what is also called the first integral, that is the Carter's constant, and this Carter's constant is related to the killing tensor field. Now, in the spacetime that I mentioned over here, the stationary axisymmetric spacetime constructed from Newman-Jennings algorithm, here as well, you have two killing vector fields, obviously, because you are considering stationary and axisymmetric spacetimes. And in addition to this killing vector fields, you also have the killing tensor field that is associated to a conserved quantity that is analogous to Carter's constant in curved spacetime. So because of this symmetries, you could write the equations governing or describing the geodesics as a set of first order differential equations rather than second order differential equations, as shown over here. Pi is a function of the conserved quantity E, L, and kappa, and the metric coefficients. Now E and L kappa are conserved quantities associated to the killing vector fields and the killing tensor field. Kappa is analogous to Carter's constant in curved spacetime. So, and U is the tangent to the null geodesics. So we can write the equations as the equations describing the geodesics as a set of first order differential equations. And yeah, and this P0, P1, P2, P3 are nothing but derivative of the coordinates with respect to the affine parameter of the geodesic. So we have equations of kind T dot is equal to something, R dot equal to something, theta dot equal to something, phi dot equal to something. Now, we can obtain trapped photons using these four equations along with a constraint. You can obtain spherical trapped photons, photons that orbit such that the radial coordinate corresponding to the null geodesic is constant. So such kind of trapped photons are called spherical trapped photons. You can obtain this from these four equations that I mentioned before by using this constraint. The first derivative and second derivative of the radial coordinate with respect to the affine parameter is 0. So it turns out that the equations that govern spherical trapped photons is a one parameter family of solution as shown over here, and this phi and q are the normalized conserved quantities. uh, so L is the conserved quantity associated to the axisymmetric killing vector field partial phi. E is a conserved quantity corresponding to the stationary killing vector field partial t, and K till this is a conserved quantity corresponding to the killing tensor field and is analogous to Carter's constant in curved spacetime. So we know how to deal with spherical trapped photons in our axisymmetric stationary spacetimes obtained from Newman-Jennings algorithm with some constraints. Now, there could be trapped photons that are not spherical. That is, trapped photons that do not have constant Boyer-Linguist radial coordinate. Now, uh, fortunately, it turns out that in the Newman-Jennings algorithm constructed stationary axisymmetric spacetimes containing trapped photons, if you have these four conditions, then spherical photons are the only trapped photons that are contained entirely in the domain of outer communications. So you don't have trapped photons that have non-constant radial coordinate. So because of this proposition, uh, now you can say for sure that you have the information of all the possible trapped photons in the domain of outer communication, because we already have the information of spherical trapped photons, and because of this proposition we know that trapped photons with non-constant radial coordinates do not exist, so we don't have to bother about such trapped photons because they don't exist. Any questions till now? Okay, we will proceed. Uh, so yeah, the next step of the proof is to study trapped photons in the phase space and study its geometry. So in the statement, if you recall, uh, the lift of the trapped photon region in the phase space is 5-dimensional. So how do you prove that? So you consider two parts. You divide the problem into two parts. First, you consider the access-free part, and you can develop this proposition. You consider trapped photons in the DOC of our space-time. The canonical image of trapped photon region in the cotangent bundle is smooth submanifold with its axis removed. So you divide the problem into two parts. First, the access-free part, and then the axial part. This is the sketch of the proof. How do you prove that the lift of trap photon region is 5-dimensional? Submanifold of the tangent bundle. You construct a function from the tangent bundle to R3, and this function should be such that if you have trapped photon or trapped null geodesic that is identified by a point in the tangent bundle, this particular point should be mapped to zero element of R3 under this map curly f. So you have to construct function of this kind. And curly f is nothing but f1, f2, f3, where fi's are functions from tangent bundle to real number. And if you define this fi's in this way, then trap photons that are identified as points in tangent bundle are mapped to zero element of R. So if you combine all this F1, F2, F3, what you have is trapped photons that are elements that are elements in the tangent bundle that correspond to trapped photons are mapped to zero element of R3. So once you do that, uh, you can prove that the corresponding differential map, that is this linear map, is has full rank. It has rank 3. Then you use the submersion theorem, which says that the inverse of zero element of the under this map curlier is a submanifold of the tangent bundle. So it is 5-dimensional because this R3 is 3-dimensional and tangent bundle is 8-dimensional, and this differential map has full rank. So you just say 8 minus 3 is 5. So 5-dimensional submanifold of the 8-dimensional tangent bundle. So this is how you deal with the geometry part of the lift of trap photon region to the tangent bundle. Now, this was just one part of the geometry parts because we removed this axis, right? We didn't consider this axis. So we have to incorporate the trap photons that are on the axis as well. So that we do in the next part, and that is considering the axial part. And for that, we have this statement. And Newman-Jones algorithm constructed stationary axisymmetric spacetimes containing trapped photons. The canonical image of trapped photons in the cotangent bundle, you consider this canonical image of trap photon, and we call it p tilde. The neighborhood of the north pole and the south pole of p tilde is smooth submanifold of the tangent bundle. So in similar lines, similar to how you dealt with the axis-free part, you can also deal with the axial part. So again, you have to construct a function from tangent bundle to R3 such that the points in the tangent bundle that corresponds to trapped photons in the space-time are mapped to zero element of R3. So if you define curly G as G1, G2, G3, where G1, G2, G3 is this, then you succeed in defining such map that throws the trapped photons to zero element of R3. And then you use the submersion theorem again. But before that, you have to prove that the linear map, the differential map corresponding to this curly G has full rank. And then you can use the submersion theorem again to to prove the statement. So that particular part, the neighborhood of north and south pole of the lifted part, is a smooth submanifold of the tangent. So this is how you deal with the geometry of the lift of trap photon region, and this proof is in lines with the proof of Sederbaum and Jans in the case of subextremal Kerr spacetime. Now, let's move on to proving the topology part of the lift of the trap photon region. So in the topology part, uh, we have the lift of the trap photon region in the phase space is invariant under partial T and rescaling of energy. So we consider only that part of the lift of trap photon region that we get after removing this particular set. So, uh, and then we aim to prove that that particular part that we denote by P0 tilde is has topology SO3. So how do you do that? First, you consider that particular part P0 tilde and prove that this slice has first fundamental group Z2. And once you prove that this P0 tilde has first fundamental group Z2, then you can use the existing results of classification of three manifolds, and you can conclude that P0 tilde, that is the slice of the total trap photon region in the phase space, is homeomorphic to SO3. So indirectly, first you show that it's homeomorphic to L21, which is then homeomorphic to SO3. So L21 is the length space that is defined over here. And ultimately, the total trap photon region, the lift of the total trap photon region is nothing but P0 tilde cross R2. R2 because you have not considered this second part. So this is how you end up with understanding the topology of the lift of trap photon region in the phase space. Any questions till now in the geometry and the topology part as well? Okay, I'll move forward then. So this is the takeaway points. In 2019, Sederbaum and Jans proved that in the case of subextremal Kerr spacetime, if you have trapped photon region, then the lift of that trap photon region is 5-dimensional with topology SO3 cross R2. This work is an extension of that work and uses the similar methodology that was adopted by Sederbaum and Jans. And this work tells that similar results hold for stationary axisymmetric spacetimes constructed using Newman-Jennings algorithm that has certain constraints on the functions f and k as shown before. And this lift has topology SO3 cross R2, which is same as that of the lift of trap photon region in the case of subextremal Kerr spacetime. The future possibilities would be to study the lift of trap photon region in other settings. So for example, in 2002, Harvey Real and Roberto Amperin gave the first uh, uh, came up with a solution of Einstein vacuum equation in 5-dimensional, which is stationary and axisymmetric. However, uh, however, the topology of the black hole horizon is not spherical, but it is S2 cross S1 in the spatial slice. Hawking's topology censorship theorem says that in 4 dimensions, the horizon topology should be S2 in the space-like hypersurface. Now, this example shows that this topology censorship theorem could not be extended in a straightforward manner to higher dimensions because you have a uh, stationary axisymmetric black hole solution of Einstein's vacuum equation in 5 dimensions that has the black hole horizon topology in space-like hypersurface as S2 cross S1. So it would be nice to study the lift of trap photon region in such settings. And other possibility is to study applications of whatever we did. So for example, how we can apply this knowledge to studying the black hole uniqueness theorems in the stationary settings. And also, we can think of how to apply this knowledge to understanding the cosmic censorship hypothesis. Thank you very much for listening to this talk. Any questions?
Okay, so thank you very much for your interesting talk.
Thank you very
And
much,
now we
Professor.
have still time for questions.
Yeah.
Have you got some comments or remarks? So I can't hear any.
So I have a,
Yes, okay.
a question.
Okay.
Yes. Yeah.
So is it so? It seems that in your proof you use, so in order to get the topology, you need to use some classification result.
Yeah.
So it means that there is no explicit description of this space.
Yeah. So if you have if you have the knowledge of first fundamental group, you can straight away use the classification results and obtain the topology. Yeah, that is it.
And how you getting the knowledge about this fundamental group?
So how do you get the knowledge of
Yeah, so
why
how you
is the
compute this?
okay. So we use what is known as the Seifert-1-Kampen theorem. So you decompose the set into simpler sets whose topology you already know, and you use this theorem of algebraic topology, and you just follow the algorithm, and you can end up with the knowledge of the first fundamental group of this.
Okay, so you're just making the decomposition. Okay.
Yeah. Using the knowledge of the fundamental group of simpler sets.
Okay, thank you.
Thank you, bro. Thank you very much.
Further questions, please? So I can't hear any. So in that case, let us thank the speaker again.
Thank you, Professor, and thank you all for listening to this talk.
And I thank everyone for the participation in this seminar. And so we close the meeting. Goodbye. Goodbye.
Bye bye.